The third question, you might see another integration that we have to do. There's, if I had to enumerate the number of ways you can integrate, there'd be many. So you use a lot of algebraic tricks that you can. Substitution is a very important part of it. You do multiple substitution at times if the function gets hard. In this case, the substitution is given, so that's a good thing. But you have to recognize substitutions at times, and in a general calculus exam, a lot of times you might not be given the appropriate substitution. Guessing or coming up with the right substitution might be the task at hand. So you have to be really, really good with a lot of trigonometric identities, because a lot of trigonometric substitutions are used for very many different functions. So let's try and solve this. If x equals tan u, dx, which is the infinitesimal on x, becomes secant squared u du. Now we can simply sub this in. I won't transform the limits yet. That is important because when you transform the domain of the function, you have to transform the limits. So 1 divided by secant squared, so it would be tan squared plus 1. Tan squared plus 1, that is secant squared. That's one identity from basic trig. So that is why I said you need to be mindful of the trig identities. So you got the secant square thing here, and then there's a square above that, and you substituted dx, it had, no surprise, the secant square. Okay, so this square gets cancelled. Now what we're gonna do is pretty simple. We have to transform the limits. Okay, as for the limits, what we have to do is rather simply, x went from 0 to 1. So what would u go from? Now u is actually, in terms of x, it's tan inverse of x. Okay, so where on the tan function, what is tan inverse of 1 and what is tan inverse of 0? We know tan inverse of 0 can be 0. That's one solution to tan inverse of 0. And what about tan inverse of 1? Tan is 1 at 45, or pi by 4. So these are the limits, and the limits can change 0 to pi by 4. And this function is secant square u in the denominator. It can become cos square u du. So you can just forget about the whole substitution. You don't have to resubstitute things at the end. Just by changing the limits, you can get rid of the whole thing altogether. Now what we need to do is find how to solve cos squared. Now for this, you can use the double angle identity. That is why I'm saying you need to be well equipped with a lot of algebra. This is something like this. So this is cos square u. You can actually write sine square u as 1 minus cos square u. That would make it 2 minus 1. Okay, so this is just a simple substitution you can do to find this formula for the double angle. So what is going to be cos square u? You can just isolate cos square u, of course. Cos 2u plus 1 divided by 2, and that's it. So the angle needs to double. Okay, if you have to switch it into a simple form in which it's not a square, it's a linear, it's in a linear form, so you have to just double the angle. So here you need to do cos 2u divided by 2 plus 1 by 2, and that's pretty much it. 0 to pi by 4 du. The rest is pretty simple. Pi by 4 0 cos 2u would have an integral of sine 2u. Okay, and there's a factor of half already, And then another factor of half would come from substitution, right? Because let's suppose 2u equals v, d 2du equals dv, and then du equals dv by 2. So you'll have another 2 over here. So that is why there's two factors of half here. Okay, and this is pi by 4 to 0. And then half, you just get a u there. U by 2, pi by 4, 0. You can just simply evaluate it. Sine 2 times pi by 4, that's pi by 2. Sine of 90 is 1. So lucky for us, this factor would be 1 over 4. Okay. Minus sine of 0 is 0, so that's 0. Plus u, that's pi by 8. So our final answer, and then 0 just doesn't give us anything. The final answer is pi by 8 plus 1 by 4.